Okay, so let's take a look at an example here where we're asked to calculate the composite modulus for a polyester reinforced with about 60 volume percent of electronic grade glass or E-glass. And we'll do so under an isostrain condition. So you can use the upper bound approach that we just learned. And we'll use data from the following tables, 12.5 and 12.6. Okay, so it looks like we need to find in the tables polyester and E-glass. And so we're going to see that the polyester that we needed here has a modulus value right here of 6,900 megapascals. We also see that the E-glass has a modulus value of 72.4 times 10 to the 3 megapascals. And so those will be the two materials we need, or two constants we need, and then we need to use the volume fraction information here. So trying to predict the upper bound or isostrain condition for the matrix. We'll do that next. I'll pause here and allow you to take a moment to try this question. And once you've got your answer, you may resume and see how we handle this one. Okay, so we had it that in the isostrain condition or the upper bound condition that the composite of the modulus for the composite is going to be based on lowercase v m, so the volume fraction of the matrix, times the modulus of that matrix. And we'll have a similar lowercase volume fraction of the fiber times the matrix modulus, the fiber modulus value. Okay, we had a moment ago that the modulus of the polyester, which is our matrix, is equal to 6.9 times 10 to the 3 megapascals. So that was the 6,900 from table 12.5. And we saw that the modulus of the E-glass, which is our fiber, is the 72.4 times 10 to the positive 3 megapascals. Okay. We also know that the polyester was reinforced with 60 volume percent E-glass. So that is to say VF is equal to 0.6, given that it must lie somewhere between 0 and 1. This also tells us that VM must equal 0.4, 1 minus that 0.6 value. So this ultimately comes together to give us the following equation, 0.4 times the 6.9 times 10 to the 3 megapascals plus the 0.6 times the 72.4 times 10 to the 3 megapascals. And after doing this, you should get 46.2 times 10 to the 3 megapascals as the composite's upper bound or isostrain modulus value. Notice that the units have worked out here. We always have units as force per unit area, the Pascal, and here we have megapascals. So we've inherited the right units given the unitless multipliers of 0.4 and 0.6 on the separate and pure component modulus values listed here and here. Okay, good. More formal version here is listed in your textbook, so those same notes are shown here. We'll do another one here, now showing that we can apply the logic here to understand not just mechanical properties, but now a thermal conductivity property. So here the question asks, calculate the thermal conductivity parallel to continuous reinforcing fibers in a composite that is 60% E-glass in a matrix of that same polyester. Okay, so notice from our diagram earlier that here there's going to be fibers. And now we're saying that the thermal conductivity is going to be different in one way versus another. Okay, so we'll call this perhaps K, the thermal conductivity value K for the composite, parallel to those fibers. Okay, we're given some data for the pure materials. So the thermal conductivity of the pure E-glass is shown here, 0.97 watts per meter K. And that for the polyester is 0.17 watts per meter K. And these thermal conductivity values and that for the question are all studied at room temperature. So take a moment to see if you can modify the upper bound equation for modulus to now instead speak to something like the composite thermal conductivity based on the individual thermal conductivity values, and try to answer the question given the volume fraction that we've handled in the previous question. Okay, so we saw that the fibers, the VF value was 0.6. We also saw that the VM, the matrix, the polyester, was the 0.4 value. Here we see that the K of the fiber, the thermal conductivity of the pure fiber, is 0.97 watts per meter K. And the thermal conductivity value for the matrix, which is the polyester, is 0.17 watts per meter K. And we want to find the composite value. Okay, so previously we had EC is equal to the V of M times EM plus VF EF. And we're now going to modify this to reflect a version that speaks to thermal conductivity. So we're going to keep our VM values and VF values, those are the volume fractions, but we'll instead now list the thermal conductivity value. So K, M, and KF. Okay, so with that, we'll go again with the 0.4 modifier on that of the matrix polyester. So that was the 0.17 watts per meter K added to now the 0.6 coefficient out front of the value for that of the fibers at 0.97 watts per meter K. Okay, and after summing that, we'll end up again with units that make sense of inherited from the two values we had. And so in this case, you should get a value that's about 0.65 watts per meter K. Okay, so again, a weighted average approach to determining the thermal conductivity value parallel to the length of the fibers in this composite. Very good. And here you see that formalized from your textbook as well. Okay, so let's speak more about these fiber reinforced composites. So as you might know, fibers are going to be very strong in tension, but they're going to be more weak in compression, so they'll kind of buckle under the compression load condition. And shear, they'll also be more weak, so that is, they will fracture in a shear across the main length of the fibers quite easily. So we have an opportunity to provide significant strength improvement in the ultimate composite when we use these fibers, taking advantage of the tension property here. So fiberglass, for example, we'll see it's a continuous filament of glass that is often housed in a polymer matrix, so a PMC in that regard. The glass fibers in this case are the reinforcement, so they are providing the strength and the stiffness to the material, whereas the polymer matrix here is what's holding the fibers in place, protecting them from the environment if needed, and transferring the load of the composite onto those stiffening agents that are the glass fiber. Okay, so fibers, being quite small, they tend to have a large fracture strength given the cross-sectional area that's quite small. Okay, so recall that the stress here is normalized for the cross-sectional area. So given that they're quite thin, we're going to have large fracture strengths for these fibers. Okay, we also benefit that because they're small, they're going to have small volume, and so there'll be relatively fewer flaws this way. And so on average, we can expect lower amounts of stress concentration due to flaws that we have touched on earlier in this course. Okay, so clearly you can see there's a logic to trying to make as small a fiber as possible by minimizing flaws, by just minimizing volume, as well as getting the cross-sectional area small so that fracture strengths are strengthened or increased. And so whiskers, for example, are a material that does this well. So these are often thin single crystals of material. They're very large in length and relative to their diameter. So that is to say they have a large length to diameter ratio. And whiskers can be made by various materials such as graphite, which again would be crystallized forms of sp2 bonded carbon, silicon nitride, or even silicon carbide. These crystals are very high in perfection, and so there's going to be maximum sort of strength properties because of this. And the downside, however, is because of their high perfection and lack of flaws and things like that, they're often going to be very expensive and can be difficult to disperse given their large length to diameter ratio. Okay, and then in another class of materials is the fiber. So here we have no single crystal materials in this time, but we'll tend to have either polycrystalline materials or amorphous materials. So note the contrast to the whiskers that were single crystal material. Fibers tend to either be polymer or ceramic in their composition. And some examples include alumina, aramid polymer, electronic glass or e-glass, boron, or even ultra-high molecular weight polyethylene. Can be used as in its fiber form for fiber reinforced composites. Okay, and lastly, we can also even consider the case where we include wires. Wires are now even larger still, so that is their length to diameter ratio is now smaller yet. And so here we're talking about wires that are metallic usually, things like steel or molybdenum or even tungsten are typical there. Okay, so fiber reinforced composites can have discontinuous fibers. And when we consider this option, we can have those fibers be random in 2 dimensions or random in 3 dimensions or even aligned. Okay, so we may have planes of materials that are showing randomness in the plane. Consider a sandwich structure built of many of these sheets of fibers in a polymer matrix. So we would therefore have randomness in the fibers within each sheet in the plane, but there would be very little randomness across the height of this structure, where most fibers have to be located within the plane from which they were once fabricated to build up this sandwich structure. So that would be a way to realize a material that's random in only two directions, but not all three directions, as the z dimension here would not be random. Okay, and alignment can be realized by things like extrusion, where as the molten polymer fiber, as it extrudes from the extruder via the die, forces would act to twist or turn fibers as they extrude through the small orifice in the extruder and would align. And often shear forces of the polymer passing through that die as well tend to direct fibers to line up to the to be parallel to the extrusion direction. Okay. And so what we want to consider now are what is conditions needed for achieving kind of low fiber efficiency versus high fiber efficiency as a function of the fiber length that we might have as an option. Okay, and so generally, as you might have expected, for long fibers, stress transference from the matrix to the fiber is going to be more efficient. So if we have very long fibers, we're going to be able to more efficiently transfer forces on the composite structure to the fibers within if the fibers are very long. In the situation where the fibers are very strong, we have less efficient force transfer to the reinforcement, the fibers in this case, to help create a high-strength material. So how do we quantify that? Well, there's an equation here that tells us that we can calculate the critical fiber length for effective stiffening and strengthening in a composite. So this is answering the question, how long does a fiber need to be to have effective stiffening and strengthening? And so it tells us that your fiber must be greater than the outcome at right, where if we knew the fiber ultimate tensile strength, so this is the highest point on the stress strain curve, and we knew the fiber diameter, okay, so that's based on selection, whatever material choice you have there, divided through by twice that of the shear strength of the fiber matrix interface, okay? So this bottom piece here, tau C, is speaking to the bonding forces between the fiber and the matrix, okay? So if you have very high bond strength between the fiber and the matrix, good, maybe even covalent linkages between the matrix and the fiber surface, the denominator will be small. This will allow the whole outcome at right to be a small, the diameter, excuse me, the denominator here will be large, which will make the whole outcome at right small, which gives you a lower bound that's quite small. So you could afford shorter fibers if you had really strong bonding at the interface between the fiber and its matrix. Likewise, if you wanted very short fiber length, you might also consider making the diameters very small so that you have high surface area to contact that matrix. Okay, and then ultimately the tensile strength of that fiber is also in the numerator there. So, good. So for fiberglass, given the typical properties that we have for including fiberglass in polymer matrix composites, PMCs, typically the fiber length must be 15 millimeters or 1.5 centimeters or greater to have effective stiffening and strengthening in the composite. Okay. So that is to say, typically, this dimension here must be about 15 millimeters or greater for effective transfer of applied load to the included fibers in the fiberglass composite.